In a previous class, we introduced the idea of the current density, conservation of current, and everything related to the current, and also we introduced the idea of resistance, right? So now we know how we can analyze a single resistor. Again, what does it mean analyzing? Three parameters: R, resistance, delta V, potential difference, and current. If you know those three parameters, you can say that you know everything about that particular resistor, right? So now we know how we can find those parameters of a single resistor. But what if you have more than one resistor? What if you have 5, 10, right, and so on resistors? How can we analyze them? Again, analyzing them, it means to find these three parameters for each of those resistors, right? Okay, so today we're going to introduce a method of an equivalent resistance, right, to analyze a circuit full of resistors. But we're going to restrict ourselves significantly. We're going to restrict to the cases where resistors connected either in parallel or in series. So this method can be used only in these cases. Of course, there are tons of situations when resistors are connected neither in series nor in parallel, and in those cases, application of this method would be illegal. Yeah, and would be, I don't know, physically mathematical criminals, right? So anyway, so let's refresh what we derived in the lecture, and then we will start looking at examples, right? Okay, so first I prepared in advance. Let's say we have resistors connected in parallel, and for simplicity, I just drew two resistors, R1 and R2, and they are connected to the battery with the potential difference delta V. So method of an equivalent resistors. In the method, you replace them with a single resistor, which we call R equivalent, right? And when you do this replacement, very important part of this method, the rest of the circuit must work in exactly the same way. In this case, it's just a battery. But of course, in real life, you can spend weeks or maybe building the rest of the circuit. And if you replace small part of the circuit, of course, you don't want to destroy the work of the rest of your circuit, right? So in this case, if delta V is across this battery, of course, exactly the same delta V must be across the battery in the equivalent circuit. And if, for example, current I is taken from the battery in the real circuit, exactly the same current I must be taken from the battery in the equivalent circuit. All right. That's how we develop this method. The rest of the circuit must not be disturbed. Right. Okay, and then what we found? First, which parameter links this resistor and these two resistors? And we found in the previous lecture potential difference. Potential difference across R equivalent must be equal, or not must be, is equal to the potential differences across R1 and R2. Right. So I can write very important piece of physics: delta V1 equals to delta V2 and equals to delta V across an equivalent resistor. This very important piece of physics we will need when we start analyzing real circuits. Okay, more or less realistic, not realistic circuits. All right, and then we also derived what? We derived the formula which can be used to find that R equivalent, right? Okay, and in this case, it's a formula which I usually don't like. I don't like dealing with those reciprocals. 1 over R equivalent equals to 1 over R1 plus 1 over R2. That's what we need from this formula, which can be used to find equivalent resistance, and this important piece of physics, right? Again, as based on my experience, students have no troubles applying these formulas, but they have troubles applying this. Okay, so now next situation. Resistors connected in series, right? And again, You replace these resistors with a single R equivalent, and again, exactly the same words. The rest of the circuit must not be disturbed. It must work in exactly the same way again. So if delta V is here, exactly the same delta V must be there. And again, if a current I is taking from this battery, exactly the same current I must be taking from the battery in the equivalent circuit. All right. And now let's write something similar for that circuit. In this case, which quantity links are equivalent and these two resistors? In this case, current. Current over there, current through equivalent circuit, equivalent resistor equals to currents through resistors connected in series. So here we had potential differences, now currents. Now I can write that I1 equals to I2 equals to I through the equivalent circuit, resistor, and then formula which can be used to find R equivalent. So R equivalent equals to the sum of the resistances of resistors connected in series. So that's what we need. All right. Okay, so after this, we can start looking at examples because the rest of the formulas which we might need today we discussed in the previous classes. Right, so this is something new, and the method is very similar to the method which a method of an equivalent capacitance. Again, in terms of step, in terms of philosophy, ideology. Right. Of course, they are different, apples and oranges, but again, the ideas are very, very similar. Okay, so it's chapter 28, and let's look at the problem 60. All right. So what do we have in this problem? Yeah, I already drew it. Right. So we have this circuit, reasonably simple. This is 12 volts. Just number 2 just overlaps with the lines, so might be difficult to see. 12 volts. 3 ohms, 16 ohms, 4 ohms, and 48 ohms. So we need to analyze this circuit. What does it mean, analyzing circuit? As I said, since this circuit is full of resistors, 3 parameters for each of those resistors, R, I, delta V. Resistances are all given. So it means that we need to analyze what? Currents through each of these resistors and potential differences across each of these resistors. Right? So let me write. So we need to analyze it. Okay, and analyzing it means that we need to find what? Oh my God. I1, 2, 3, 4. All those currents and potential differences across each of those resistors. Right? So delta V 1, 2, 3, 4. So we have 8 unknowns, right? Okay, so and the method, as I said, will be very similar to the method of an equivalent capacitance. So I'm going to even arrange everything in a very similar way. Right. Okay, so I'm going to draw circuits somewhere in the middle, maybe slightly shifted to the right. And then on the right side and the left hand, on the left side, I'm going to write calculations. But first, some students might be confused when they see resistors drawn like this diagonally. Because every time, all the books, in all the analysis, every time we drew something like this, if resistors connected in parallel, we drew them like this, right? So on top of each other, right? So, and everyone sees, okay, these are parallel. Or if we drew them like this, okay, everyone sees that they are connected in series. But once we shift to diagonal, resistors position diagonally, some students don't feel comfortable. But we need to remember that the way we draw it, it's maybe pleasant from this aesthetically, right? But we need to look at resistors from the point of view of physics. What does it mean when resistors connected in parallel? It means that the potential difference across those resistors must be exactly the same, no matter to which circuit you connect them. potential difference across resistors must be the same. Or you can connect bulbs or motors or maybe people, whatever, right? Any elements. If potential differences across elements exactly the same, it means they're connected in parallel. So let's see about, for example, these resistor R2 and resistor R4. Guys, if you have questions, right, don't try to use chat. Ask me directly, right? So because it's difficult to read the chat because it kind of loses, can lose the my thoughts and so on. So what about this resistor and this resistor, R2 and R4? Because right now they're not drawn like this. But let's look at the potential difference across them. Look, over here, this point and that point, sort of above the resistors, are they at the same potential, electric potential? Of course, they're exactly at the same potential because basically these over here are just one big solid piece of metal, which doesn't have resistance and which is at exactly the same potential. So all these points on this wire, this piece of wire and this piece of wire, they are at exactly the same potential. Maybe let's say 9 volts or maybe 6 volts, whatever. Now let's look at this point and this point, right, on the other side of these resistors. Since you see they belong to this one big solid piece of metal, because wire is a solid piece of metal, right? And in this case, it's an ideal wire which doesn't have any resistance, right? So again, all these points are at exactly the same potential. Okay, different than above, but over here it's the same potential. Let's say maybe here it's 3 volts. So here 6 volts, here 3 volts. So potential difference across these two resistors are going to be exactly the same. So 6 minus 3, it will be 3 volts, right? I'm just making it up. Right? So you see, these R2 and R4 actually connected in parallel. Of course, I can redraw the diagram in order to make it more comfortable or more convenient for our eyes, right? But it's not the whole story. What else? What else can we say about this R3? It is also connected in parallel with this R4 and R2. Because again, potential above this resistor over here, this equals to the potentials above those two resistors, and the electric potential sort of below this resistor over here. Again, you see it's just one solid piece of metal. It's exactly the same as electric potentials below this resistor and that resistor. So these three resistors, 2, 4, and 3, they're connected in parallel because potential differences across them will be exactly the same. It doesn't matter which battery you will connect over here. All right, see that? So now let me redraw it so that it would look, actually it looks nice, symmetrical. I like this diagram, but we can redraw it so that it would be more convenient for us, right? Okay, so now let me redraw it this way. Okay, I will probably, as I said, move slightly to the left, to the right shift. Right. Is this circuit and that circuit, are they the same? Yeah. Physically, they're exactly the same, identical. Of course, I need to write down the, this is R1, this is, which way I label in my, this is R2, R3, and R4. So that circuit and this circuit, exactly the same. Of course, we drew them differently, but from the physical point of view, no, from the point of view of physics, they're identical. And that's what I just discussed. These three resistors are connected in parallel, right? Okay, if you still have any doubts, tell me, right? Because now I think we discussed it enough and it should be clear, right? Okay, so now we just discussed they are connected in what, in parallel, right? So now let me make the first simplification. So these 3 resistors connected in parallel, so I can redraw my circuit. All right. So it will be R1 still untouched, and now instead of those 3 resistors, I'm going to introduce a single equivalent resistor, and of course I'm going to label it as R sub 234 because we replaced those resistors. 2, 3, 4. All right, and R1 of course is untouched, and I didn't label the battery. The battery still works in exactly the same way, right? So you see, similar steps I've done when we analyze capacitors. Now we applied a very similar method for resistors. Okay, and now of course we need to start calculating this R234. Of course, what we need to use this formula, which I usually don't like applying. Right, so 1 over R234 equals 1 over R2 plus 1 over R3 plus 1 over R4. And again, reminding you, every time somewhere on the second or final exam, I don't know, like 5% of students, they calculate this, but then they forget to flip to take a reciprocal of 1 over of this, right, of the number, to get actually resistance. So they use still 1 over R as the value of the resistance. Don't make that silly mistake. Right, okay, so of course you can plug numbers. Okay, maybe I will write, so it's a 1 over 16 plus 1 over 4 plus 1 over what, 48. Oh my god. So anyway, so you can easily calculate, bring to the same denominator easily. All right, so R234 will be just not 4, 3, where is it? 3 ohms. Right, 3 ohms. Okay, let me frame it slightly because at some point I will need it. Okay, so that's the first step in simplification. Now we need to simplify one more time because now it's obvious, right? So that these two resistors connected in series, right? I've never seen a student who would doubt this so far, right? Because it's exactly what we have here. So these guys connected in series. So the final step in simplification. And now I can draw the final circuit, the simplest one, where we have final R equivalent. And again, battery still works in exactly the same way. Right. So exactly the same delta V of 12 volts is applied across this R equivalent. Of course, we can find this R equivalent because those two resistors connected in series. So I can write down, so R equivalent equals to R1 plus R2, 3, 4, right? R1, 3 ohms, this also 3, so R equivalent, 6 ohms. Okay, awesome. Right, now I need to remove this. And now we have the simplest possible circuit. Can we find current, for example, taking from this battery? Piece of cake. Ohm's law. Now we need to use stuff from the previous class. Ohm's law, right? So now at this point, after we manage to simplify the circuit, now we can find the total current. So total current taking from the battery we can find. So now we can find, and let me call it I equivalent, sort of to connect, to relate that this current flows through this equivalent resistor. But of course, we also know that it's a total current taking from the battery. So it's a delta V divided by R equivalent. Delta V is 12 volts, right? Divided by 6 ohm equivalent resistance. 6 ohms, so it will be 2 amps of current. Okay, let me circle it in red because it's important step. So basically, that was effectively, this was our goal in simplifying this circuit, because this is the total current. Again, as I said, if This is the total current in our equivalent circuit. Exactly the same current is over here because we replace in such a way equivalent resistance, introduce in such a way so that the rest of the circuit is unchanged. And exactly the same I here, right? So we simplify circuit, we managed to find the total current, and that was at least now we have at least something. If I asked you from the very beginning over here, what's the total current taken from this battery, you would have troubles answering that question unless you are very, very experienced and you've done this many times. Probably you should, maybe some of you can answer it immediately, but I doubt that I would be able to do it, right? So now at least we found at least something, and now it's sort of like I told you, it's sort of like a crack in the wall. We've created small crack, this total current, and now we need to expand that crack in order to see the truth, right? All that information, to see the whole truth, right? And nothing but the truth. And now, once we got this, we can start moving backward, finding what needs to be found. Right. Okay, so now let me use a red to go back, right? So, and now let me write. So now, go back. Now, start moving. And so now we need to use these pieces of physics. So to simplify, we use these formulas. Now we need to use these pieces of physics to start moving back. So I usually call them like bridges. Bridge to go from here to there and then from there to there. So this resistor replaces resistors connected in series. Series case, currents are the same. Current through the equivalent resistor, which we just found, will be equal to the currents through these two resistors. So that's the bridge which we need to apply now. Okay, let me write it down. Right, so I1 equals to I2, 3, 4 equals to I equivalent equals to 2 amps. And let me remind that this comes from there, right? So that's the bridge which we need to apply, right? And now look, for example, resistor R1, we know its value, we know the value of R1, 3 ohms, we know current, we can find the potential difference, delta V1, which also needs to be found, right? So now I can write, so delta V1, oops, not wrong, delta V1 equals to R1 times I1. And again, as I told you, I1 comes from the bridge because it is equal to the total current, actually, 2 amps. Right, so it will be R1 is what? 3 ohms times 2 amps. It will be 6 volts. Okay, sorry, 6 volts, right? 3 ohms times 2 amps, 6 volts. So that's the potential difference. Now we can say, okay, we know everything about R1. We know it's the value. We know the value of R1. We found current 2 amps, and now we found potential difference. Analysis of resistor R1 done. But we still have R2, 3, 4. Inside of that resistor, there are still plenty of hidden information. So now let's find the potential difference across 2, 3, 4, right? So of course it will be R2, 3, 4 times I2, 3, 4. Resistance. We found the value of resistor. And current, of course, again, comes from the bridge, 2 amps. So again, it will be 2 times 3. So it will be 3 ohms. 3 ohms times current 2 amps, right? Again, so potential difference 6 volts. So potential voltage drop across both of these resistors exactly the same. 6 volts, and of course makes sense. It gives us total 12 volts, which is provided by the battery, right? Okay, so we exhausted. We used everything that we can from the first bridge. Now we need to go back to the last to the first circuit, because inside of this R23 we have those three resistors, right? And now those three resistors connected in parallel, so we need to use these bridge potential differences across. This resistor must be equal to the potential differences across those three resistors. So let me write that down, bridge that. So it will be delta V2 equals to delta V3 equals to delta V4 equals to delta V2, 3, 4 equals to, where's my delta V2, 3, 4? It's here, 6 volts. So 6 volts goes up there. You see, everything is linked, nicely connected, right? So 6 volts, right? Maybe I should show somehow. So this delta V234 goes over there, right? Okay, so and now let's start milking this bridge, right? So let's try to get all possible information. First, potential difference across the second resistor. Yeah, we have, and we know the value of R2, so we can find current again using Ohm's law, right? So as a result, now we can write I2 equals to delta V R2 divided by R2, right? Yeah. Okay, delta V2 6 volts divided by R2 16 ohms. So it will be, oh my God, what, 3/8, 3/8, right? Let me check. Yeah, 3/8 of an amp, right? So now we can say we finished analyzing resistor R2. Potential difference we found, current is found, value of R2 was given initially, right? So done with R2. Now current through the third resistor, this one, exactly the same, delta V3 divided by R3. So 6 volts divided by the value of R3, 4 ohms. So it will be 3/2 amps, 1.5 amps. So that's the value of the current. So now we finished analyzing resistor R3 and now R4. So now let's find the current, delta V4 divided by R4. And again, all these delta V's, of course, they come from the bridges, right? So now, right, so delta V4, 6 volts divided by, oh my God, 48 ohms, the value of R4. 108, 1/8, right? 6 times 8, 48, yeah. 1/8 amps, right? Am I correct? Absolutely. Okay, so now we also know the value of current through the resistor R4. Done. We found all those I's. We found all delta V's. Now, problem is solved. Again, you see structure is very, very similar to the structure which we used to analyze equivalent capacitance. But now, of course, formula is slightly different, but ideology is very, very similar. Okay, all right. In my lectures, I posted another example with 3 resistors, so you can look at that example by yourself. Because again, similar to the equivalent capacitance, so you should be able to do it by yourself. Of course, there will be similar problem in your homework. Okay, any questions, concerns, or maybe you got lost somewhere? I think I've been trying to be as diligent as possible. Right. Okay, so if you are quiet, right? But again, if you need extra explanations, don't be quiet. Don't be very loud, but All right. Okay, so now then next problem is 16. All right. So what do we have in problem? Okay, 28, 16. 28, 16. Three resistors are given. And we know the values of two of them. The third one, I don't the labeling was erased. I don't know, is erased. So we don't know the value of the third resistor. We actually need to find the value of that third resistor. Right, so now let me draw a situation. So probably I will draw it here. So let's say we have resistor number 1, then resistor number 2. And, okay, let me step away slightly more. And then resistor number 3. So values R1 10 ohms, R2 15, and R3 is our unknown. In your homework there will be similar problem, but resistors will be connected in parallel. Right now they are, you see, in series, but in your homework they will be connected in parallel. But so the idea to the solution will be very similar. But it's not the whole story. What else is given? We know that current is flowing through them, and the value of the current is given, 100 milliamps. And even this is not, even more than that is given. So the potential difference across the whole structure, delta V, is given 5 volts. Okay, now that's what we have. And we need to find R3. Okay, so of course some students can actually, I'm sure that some of you can start solving the problem without maybe additional push. But let me apply what I like. Let's write down everything that we can about this system, about this circuit. Of course, from the point of view of physics, right? And since this circuit is full of resistors, right? And of course, if you want to know everything about resistors, you need to discuss 3 parameters again: R, I, delta V. So let's write down everything that we can about these 3 parameters, right? Let me write over here, maybe underneath. All right, 3 parameters again, in order to see all possible methods that can be used to solve this problem. So let's start with what? With current. Yeah, let's start with current. All right. So what can we say about current through these resistors? These guys are connected in series, obviously, right? So current is the same. Or you remember conservation of current, which we discussed in the previous, no, not in the previous lecture before. Since we don't have any junction points, it doesn't matter where you measure your current will be the same. So this value of current is exactly the same in each of these resistors, right? Conservation of current when there is no any junction points. So I can write down the first piece of information. So I1 equals to I2 equals to I3 equals to 100 milliamps, right? Okay, I'm not going to write the value, but obviously, right, 100 milliamps. I'll just want to write, okay, let me write I, why not? Then what's next? Delta V. What can we say about delta V? I think, again, it's more or less obvious that the total voltage drop across the whole structure must be equal to the sum of delta V1 plus delta V2 plus delta V3. Right? Again, usually students don't have problems with that. So I can write, so delta V1 plus delta V2 plus delta V3 equals to the total voltage drop, which is actually given. So that's what we can get about delta V. And the last parameter, R, resistance. Nothing except for, yeah, we can try to bring into the game R equivalent, hoping that it might help somehow, right? So we can go through R equivalent. And in this case, of course, R equivalent will be what? It's a this. Yeah, connected in series, so it will be R1 plus R2 plus R3. So these what we can extract about these three parameters. And of course, every time we need to also use the formula which connects all these parameters, right? Ohm's law, right? Similarly, I drew when we analyze capacitors, right? Now, all right, resistors. So now I have to use Ohm's law. Yeah, R equals delta V over I. Right. So this is the whole package. We cannot add anything else to this. And now, so let's try to identify method which can be used to solve this problem. First method, again, this is important piece of physics about currents. But of course, from here, just by itself, we cannot get information about the resistance, right? So we need to use either this equation or that equation. So let me call it the first method will be based on the equation on this equation about potential differences. And of course, we will have to use, of course, you know what? Let me move this information to the side. I will rewrite it here. All right. So the first method will be based on this formula with this important piece of information, and every time formula connecting all three parameters. So this will be method number one. Method number two will be based on the formula for the equivalent capacitance. So let's say this. And of course, information about current and the formula connecting all these formulas will be used. So this will be method number two. So these are two methods which can be used to solve this problem. So let's apply both of these methods. Yeah, I promised to rewrite delta V. So delta V equals to 5 volts. Okay. All right, so let's start with the first method. Okay, since I use blue, let me write 1. Which is based on this. So let me rewrite the formula for delta V, of course. Delta V1 plus delta V2 plus delta V3 equals to the total voltage drop. We need to find resistance at the end. So we need to bring into this formula the values of resistors. And of course, that can be done through this formula, through the Ohm's law. Right? So we can write this as R1 times I1 plus R2 times I2 plus R3 times I3 equals to delta V. So we just use Ohm's law, right, from the method number one. And now it's time to, of course, to apply the first piece of information about the current. All these currents are the same, right? So it's I, and I. So now we can use, of course, the fact that currents are the same. So we can factor that out. So I can write I times R1 plus R2 plus R3 equals to delta V. Okay, so pretty much what? Only one unknown in this equation, R3. The rest is given, right? So we've applied all physics at this point. Now we just need to solve this equation for R3. That's it, right? So I can probably rewrite it like this. I take this current to the right-hand side. In the denominator, I will move it. So it will be R1 plus R2 plus R3 equals to delta V divided by current. And so, again, this is our unknown. So let's move currents. I mean, the R1 and R2 to the right-hand side. And as a result, we will get R3 equals to delta V over I minus R1 and minus R2. Delta V 5 volts. Current is 0.1 amps minus 10 ohms. 10, yeah, and minus 15 ohms. So here we have 50 minus 10, 40 minus 15. It's 25, yeah, 25 ohms. So the answer is 25 ohms. So that's the value of the current. Oh, yeah, the value of the resistor, R3. All right. Okay, good so far. Again, if you need, if you have questions, or if something is confusing, or maybe in terms of handwriting, just tell me immediately, right? Unmute myself and say something. Okay, now I need to erase this, and now method number 2, which is based on R equivalent. Okay, I don't want to erase that, so let me just separate with the long line, right? Okay, so now method number 2. And as I said, now it's based on R equivalent. So let me rewrite this formula. So R equivalent equals to R1 plus R2 plus R3. Okay, so let's look carefully at this equation. How many unknowns do we have here? R3, it's our final goal, right? So it's unknown. And also R equivalent right now is not known. So we have 2 unknowns in one equation, which is not good. And since this is our final goal, that's what we need to find at the end. So it means that somehow we need to find R equivalent. So our first step must be, right? So how can we find R equivalent? Because usually up to this point, every time we use these formulas, right, to find R equivalent. But we're trying to use it, but we have unknown R3. So we cannot find R equivalent using the formulas which we derived, right? So R equivalent must be found somehow else. How? Look, using electrical these parameters which is given. Let me very often students don't see how R equivalent can be found. Let me draw an equivalent circuit, and after that usually the students everything becomes clearer, right? So let me draw equivalent circuit. So let's say this will be our R equivalent, right? And then the battery, right? And you remember the method when you replace the actual resistors with R equivalent, the rest of the circuit must work in exactly the same way, right? So what about potential difference? Potential difference is 5 volts. It's basically, I can draw that here some kind of some fake battery, right? Of course, the battery is not given in the diagram, but I can easily add it, right? So this potential difference, of course, is provided by something. Let's say it's this battery, so 5 volts battery. And when we introduce the equivalent resistance, right, that battery, which is this here, right, must work in exactly the same way. So exactly the same 5 volts must be provided by this battery across our R equivalent. So this will be the same. Delta V equals to 5 volts, right? Then, of course, this current I, of course, provided by this battery, right? And again, the same current must be in our equivalent circuit because the rest of the circuit must work in exactly the same way. So exactly the same current I, which is 100 milliamps, flows through our equivalent resistor. And now, once we identify that, if I ask you, so how can we find R equivalent? Everyone sees that, right? So it's just delta V divided by current. So that will be the value of R equivalent, right? So let me write it down. So from the equivalent circuit, we can find that R equivalent equals to delta V divided by I, so which is 5 volts. You know what? I don't want to plug numbers, right? So, of course, you can calculate R equivalent. All right. I just want to get an expression. So now I can, of course, plug this R equivalent instead of R that. And as a result, we will get so delta V divided by I equals to R1 plus R2 plus R3. And something similar we've seen over here. It's exactly this equation. All right. So let me connect that this and this, right? So they are exactly the same. Right, so that and this. So it means that, of course, you can solve it for R3 in exactly the same way. So, of course, you can get from here R3 equals to 25 ohms. Right? So that's how I would address this problem. Although my sort of out of these two methods, I would probably use method number 1. In this case, R equivalent, it's sort of like you add an unnecessary complexity. Again, nothing wrong with R equivalent. In this case, it's just like using a heavy equipment to solve simple problems, right? R equivalent is useful in the example which I just erased, right? But in this case, I will just use method number 1. Again, as I said, in your homework, there will be very similar problem, even with values of resistors will be exactly the same, but resistors will be connected in parallel, right? So you will, again, you can identify two methods, right? And you can use either that or this, right? It's up to you. So structure, ideology will be very similar. But of course, in that case, if resistors connected in parallel, what will be the same? Not currents, but potential differences. Right? And currents are going to give you an equation. Right? And then, of course, if you want, you can also play with R equivalent if you want. But again, the value of R equivalent you could find, you will be able to find if you want from an equivalent circuit. Okay, so yeah, I was dreaming about solving additional problem, finding R equivalent of some reasonably complicated circuit. We will do it on Wednesday. It's not the end of the week, right? So we still have Thursday. No, Wednesday, right?